Okay, what we're going to do here is try to make a table of data and graph for log base 0.25 of x, and also try to use it as an opportunity to just keep reminding ourselves of the notation and what everything means, etc., etc. Now, the idea with any logarithm function and most logarithm problems that don't specifically use the properties that we haven't gotten to yet is to constantly try to go over to exponential functions, do the hard work with exponential functions, and switch the x and y back. For example, if we write down that we're trying to find y equals log 0.25 of x, remember that's exactly the same thing as saying 0.25 to the y equals x. That's still the logarithm function, but what we want is to go back to the original exponential function. Now the original exponential function is what you get when we switch the x's and the y's. So let me write original right here. And write down the original. What I'm going to get is y equals 0.25 to the x, like that. We can make a table of values of this without breaking too much of a sweat. What I'm going to do is try to squish that a little bit in here so I can have lots of room for graphs. I'm going to get x and y, and just the usuals, minus 2, minus 1, 0, 1, 2, like this. Now how does this work? I'm going to plug in 0 and get 1. I know that every time x goes up by 1, I keep multiplying by 0.25, right? So this is going to be 0.25, this is going to be 0.25 squared. Now, from here to here, I divided by 4, so from here to here, I multiply by 4. So I'm going to get 4 here and 16 there, like that. Now, that is the original exponential function. And just a reminder what that graph looks like. This graph looks like, I'm going to put this down here because I want to save all the big room for the other stuff. The original, this is a decaying exponential function. It goes like this. Now remember, this is not the graph I'm after. That's the exponential function. So we're looking at the original exponential function, graph looks like that. We're looking at the original exponential function, the data looks like that. Now, how hard is it to get the data we want? Well, we just switch the x's and the y's. That's not going to kill us too much. Let's put this down here. So what I want to do right here is to put, if I can, okay, we're going to go like this. How about this? X, and then instead of the exponential function, we want its inverse, which is this. But we don't have to think hard to get. We just need to switch all these x and y values. So, and this is going to be minus 2, minus 1, 0, 1, 2. And over here, I'm going to get 0.25. Oh, no, I'm going to get 16, sorry. 16, and 4, and 1, and 0.25, and 0.25 squared. So we can get data for the log function just by going back to the original exponential function and switching the tables, which is really, really nice. If I want a graph of the log function, now we can just plot the points and connect them up, but we should also make a couple of things notice, by the way. In the original exponential function, the y's are always positive. The y's are never negative. So when we switch the x's and the y's, instead of saying the y's are always positive, we're going to say the x's are always positive, so there's going to be no graph back here for the log function. Now, this point right here is the 0.01, so the 0.10 is going to be on the log function. You can see that over here, the graph is getting very close to the positive y-axis. That means over here, the graph has to be getting very close to the positive x-axis. It's going to come down like this. And finally, if you look at this thing over here, you can see that over here, the further I go out into this quadrant, the more and more parallel the graph here comes to the positive y-axis. That says over here, over here is going to be more and more parallel to the positive x-axis, and you're going to get a graph that looks like that. So we can get a graph of a log function, we can get a table of data of log function without ever actually having to think about what a log was, except that it was the inverse of an exponential function. Now, how did we do this? We just wrote y equals, and either we remembered that it was the inverse of an exponential function, or we just did what they normally do in an algebra class. We took this, we wrote it as an exponential form, and then we switched the x's and the y's. We now have the original function. We know what the original function looks like. We spent time on that. We know what the original function's data does. We had time on that. And so to get the inverse, we switched the x's and the y's, and we get a table really easily. And to get the graph, we can either plot the points, or we can remark there are three important things about this. The point 0, 1 was on the original, so the point 1, 0 is on the new one. The y's are never negative over here, so the x's are never negative over here. And up here, the graph becomes more and more parallel to the positive y-axis. So over here, the graph becomes more and more parallel to the positive x-axis. So that's how we get a table of data and a graph from a log function without having to think too hard.